So looking at spontaneity and standard potential. So you're going to be dealing with an oxidation and a reduction, right? You're thinking about some reaction where something's oxidized, something's reduced. You look up you look at the table and you figure out what the reduction potential is of the reduction half reaction. You figure out the oxidation potential for the oxidation half reaction, and you add them together. For the oxidation, you're just taking the value on the chart and reversing it. If the value is positive, it's spontaneous. That's it. If the value is negative, it's not spontaneous. So you might get a question like this sometime. Which of the following species will be oxidized by 1 molar hydrochloric acid? So if you've got HCl, right, this is a species being oxidized. So here we've got some metals, we've got fluoride. These things, we'd be taking electrons off of there. So whatever we see on the chart of reduction potentials, we're reversing it because we're looking for oxidation. A note real quick about the HCl. You've got H+. H+ can be reduced, right? But Cl- cannot be reduced. So we're only looking at H+, and H+, this is 0. The standard reduction potential is 0. All the other values that you see on the table are compared to this. So these are all relative values. So this kind of makes our adding up a little bit easier since it is 0. Well, let's look. Gold, giving up its 3 electrons, is negative 1.498. Well, plus 0. So that's not spontaneous. So no. Magnesium. All right, we have a positive potential. I should write volts. All right, we have a positive potential here. Yes. Plus 0 is still a positive potential, so that can be oxidized by 1 molar HCl. Copper. Now, copper appears on your chart twice, so you might want to consider each. Well, copper can be oxidized to Cu2+. That's with a potential of 0.339, so that's possible. Cu can also be oxidized to a +1 ion, and we see a 0.518, so that's also possible. Fluoride being oxidized to fluorine gas is negative 0.2 or 2.889, so that is not going to happen. You're not going to be able to do that. So that's just, you're not doing it. All right, so those 3, the answer is yes. Well, I just have another question here. What about something like, what is that? Minus. What about something like nitric acid? Nitric acid not only has the H+, but it also has nitrate, which is itself an oxidizer, which means nitrate can be reduced. Right, so here's another thing that you find on some charts, but not on others. So nitrate and 4 protons plus 3 electrons yields nitric oxide and water, and we get 0.964. So some metals would be more likely to dissolve in nitric acid because of the nitrate, and because we can see that the potential is greater to strip things of their electrons. In this case, I don't see anything changing because nothing was less than negative 0.964. So if something was like negative 0.5, then I would say, yeah, in nitric acid, you can do that. But fluoride and gold doesn't work. You may say, wait, Mr. Poot, I thought I heard something about aqua regia, right, where we have this mixture of nitric acid and hydrochloric acid, and this can actually dissolve gold. So, so if we look at these reduction potentials, we can see, right, here's a reduction, here's a reduction, here's 2 oxidations. So we have 2 oxidations, we see the potentials are negative. But that's not going to happen, right? But this one looks a little bit more likely. We have negative 1.001. We can see that the oxidation potential of gold in the presence of chloride, right, is much, well, it's better, right? It's better. It's close to this. It still looks negative, right? The reduction potential of nitrate. But look what the nitrate needs, right? The nitrate needs 4 moles of hydronium per mole of nitrate to do this, to take these 3 electrons. So you can kind of see why you would need hydrochloric acid mixed in there and a bit of nitrate. So I think it's 3 parts or 4 parts hydrochloric acid to 1 part nitrate. But if we add them together, we still get a negative value. That's where the Nernst equation would come in. Right? If we think the standard potentials are all at 1 molar, but we can see on the reactant side, right, we have this concentration of chloride to the 4th, which is going to be in the denominator. We have a concentration of hydronium to the 4th, which is in the denominator. And then we have nitrate, which is also in the denominator. Gold here is a solid. This is aqueous. Right? We have a complex ion. And this is going to be a gas. It gets bubbled out. So we have 2 things appearing in the numerator, but we have 9 aqueous species in the denominator. So if you drive these concentrations up a whole lot, then your Q is going to go down, and the potential would get a little better. So again, these are for 1 molar. We're not going to have 1 molar of these. Right? This is a gas. This is going to bubble out of solution. So, or 1 atm of pressure above the solution, I guess. So aqua regia, you can see from your standard reduction potentials how this can be possible along with a very low Q value because the concentration of reactants get quite high.